The planets, air, water, rocks, plants, animals, human beings. Absolutely everything in this universe consists of tiny particles called atoms. Today, human growth and welfare is driven with the energy produced from these very tiny atoms and their interactions. Do you know what this atom is made of? Let's peep in. The atom has a nucleus at its center, containing protons and neutrons, while electrons revolve around the nucleus at very high speeds. These protons and neutrons are held together by nuclear forces. When this nucleus is split, enormous energy is released. This energy is harvested by a nuclear power plant for generation of electricity. How can we generate electricity from an atom? Are you curious to know how all this happens? Let's take a tour of a nuclear power plant. A very rare opportunity for all of you, since a nuclear power plant is a highly secured zone. This three-dimension animation is the simplified replica of a 540 megawatt pressurized heavy water reactor, or PHWR. In this virtual tour, we will take you through various processes of a PHWR. So friends, get on board and get ready for an exciting and unforgettable journey. Let's count down. Identity check, authorization of person, no electronic devices, photo pass formalities. Nuclear power plant mainly comprises of a reactor building, turbine building, control building, auxiliary building, pump house, switch yard, stack, waste management facility, and essential supporting facilities. It's constructed near a large water body like sea, river, etc. Unlike thermal power stations that use fossil fuels like coal, the nuclear power plants generate electricity from the energy released from fission process of uranium or plutonium nucleus. Let's go and take a look inside it. The two dome-shaped structures seen here are the reactor buildings, and the rectangular structures on the side are the turbine buildings. The entire operations of the nuclear power plant are controlled from the control building. Let us first know about the reactor building and its systems. The reactor building is a tall and rigid structure with a height of about 50 meters and a diameter of 56 meters. A speciality of the reactor building is that it is kept at negative pressure, that is, lower than the atmosphere outside, to ensure that air flows in and not out of the building, thus containing radioactivity within the building. This round-shaped building is made of two enveloping walls, known as the inner and outer containment walls. These walls are separated by a gap of about 2 meters. Like inside the reactor building, the gap between the two walls is also kept at negative pressure to prevent any radioactivity release to the atmosphere. The inner containment wall and dome are of pre-stressed concrete, while the outer containment and domes are RCC structures. Inside an actual reactor building, there are several intricate systems, equipment, pipes and cables. But this simplified view shows only the most important parts like calandria, primary coolant system, moderator systems, steam generators, reactor shutdown systems and control rods. Let us begin with the calandria, a horizontal cylindrical vessel in the center of the building, which is also the heart of a nuclear power plant. In fact, the nuclear fission occurs inside this vessel. The calandria is made up of high-grade stainless steel with a diameter of about 5.9 meters and a length of 7.8 meters. The stainless steel components that are connected at either side of the calandria are called end shields. These end shields act as a shield, preventing radiation from coming out. The calandria is filled with heavy water, which acts as a moderator to slow down the neutrons produced in the nuclear fission chain reaction to desired energy level. A set of pipes called coolant channels pass through the calandria and end shield assembly. The metal used for these pipes is an alloy of zirconium and niobium. 392 such coolant pipes exist in a 540 megawatt BHWR. Each coolant assembly, in fact, has two concentric pipes, one inside the other. The outer pipe is called the calandria tube, while the inner pipe is called the coolant tube or pressure tube. For thermal insulation, carbon dioxide is filled between these pipes. The coolant tube has mainly two things inside. One, the heavy water flow that helps to transfer heat to the steam generator. Two, the fuel bundles that generate heat by fission process. Loading new fuel into or removing spent fuel from the reactor is carried out by two fueling machines at both ends of the calandria, which are computer controlled. The loading is done through remote operation as a radiation safety requirement. In EHWRs, the fuel loading is done while the reactor is in operation. This online fueling helps maintain reactivity, power levels and symmetry. As a result, the coolant also moves through the reactor in both directions. Let us now understand how the fission process takes place in this BHWR. The loaded fuel bundles consist of natural uranium, which is a common element found in the earth. The uranium extracted from ore is converted into yellow cake, then to uranium dioxide powder, and then formed into pellets. But how is it used as a fuel? Let's get some awesome basics. Natural uranium has two types of atoms or isotopes, namely U-235 and U-238. Among these two, the U-235 is the fissile material. When this fissile material is struck by a slow neutron or a thermal neutron, it will split into two or more fragments. This splitting is accompanied by tremendous release of energy in the form of heat and 2 or 3 fast neutrons. These fast neutrons are thermalized or made to slow down by the moderator in the calandria, so that they have a high probability of hitting other U-235 atoms and are at the right energy level to cause fission, thus causing and sustaining a controlled chain reaction that releases more energy and further sets of neutrons on fission. The continued fission reactions produce tremendous heat. In order to maintain the heat at a particular desired level, the fission reaction needs to be controlled. This is done by control rods. These control rods, made of cadmium or cobalt, absorb the neutrons. By raising or lowering these rods, the rate of reaction is controlled. Thus, in a nuclear reactor, a controlled, self-sustaining nuclear fission chain reaction is achieved which produces heat. The flowing heavy water inside the coolant tube transfers this heat to the 4 vertical cylindrical steam generators that are placed at a higher elevation. Upon receiving the heat, the light water flowing in steam generators in secondary circuit converts into steam. The steam raised in the steam generators is taken to the turbine in the adjacent building through the steam pipes. The turbine generator assembly or turbo generator in a 540 megawatt PHWR has 1 high pressure turbine and 2 low pressure turbines. The steam produced in the steam generators upon reaching the turbine rotates it at a very high speed of about 3000 revolutions per minute. The generator coupled with the turbine also rotates and generates electricity. This electricity is transmitted through the switchyard via high-tension transmission lines to the grid. From this grid, the electricity is distributed to consumers, and thus we get electricity for our homes and industry. Now, let us go back to the nuclear power plant to know about the safety systems. Back in the Calendria and the reactor building, there are 2 important systems for safe shutdown of a reactor: shut-off rods and the secondary shutdown system. The control rods are used to maintain the desired power level of the reactor during operation and to shut down the reactors when fully inserted. The secondary shutdown system, which is based on addition of neutron absorber into the moderator, helps to bring the reactor to safe shutdown during normal and emergency situations. There is also a suppression pool located at the bottom of the reactor building. It is basically a large reservoir of water used for long-time cooling of the reactor core and suppression of steam and radioactivity in emergency situations. All the operations of nuclear power plant are carried out remotely by operators in the control room. Nuclear power plants are designed, constructed and operated in such a manner that there is no undue radiation exposure to the personnel, public and the environment. We are constantly exposed to natural radiation from various sources, and people receive insignificant radiation from nuclear power plants as compared to this natural background radiation. Most of the radioactivity remains within the fuel itself, which is the first barrier. The cladding of fuel forms the second barrier. The primary coolant system is the third barrier. The reactor building is designed with a double containment wall that contains the radioactivity within the building. This forms the next barrier. There is also an exclusion zone around the plant where no habitation is permitted as a measure of caution. These barriers create a safe atmosphere for the people residing near the plants. This principle is known as defense in depth. There are many other safety systems engineered in the nuclear plant to ensure a very safe operation of the reactor. They work on the principles of fail-safe, redundancy and diversity. The entire operation of a nuclear power plant is controlled through qualified, trained and licensed operators. The possibility of human error is minimized by installation of automated computerized systems. Special attention is paid to the environment around every nuclear power plant. Conscious efforts are focused towards study and conservation of biodiversity, flora and fauna. The lush green surrounding becomes a happy habitat for many different species of birds and animals. Friends, nuclear power has several merits, the most important being a carbon-free, sustainable and intense source of energy. Nuclear energy has the potential to contribute to the growth of our nation by supplying the environmentally benign power safely, reliably and economically, thereby bringing happiness to the people and prosperity to the nation.